So this should be a fun and heady conversation that I think may affect the way you view the near-term possibility for quantum computing. And I think it's really incredibly important. So we're not going to explain what quantum computing is. If you need more background, there's dozens of beautifully animated explainers on YouTube. You can even watch Canadian Prime Minister Justin Trudeau explain it at a press conference. It's quite a watch. As we've heard the last couple days, solving some of these critical business and social problems depends on a better way to approach computing to deal with all the data coming from all these critical flows. But we're kind of at this weird interstitial moment where we can see all these promising new computing architectures like neuromorphic computing or photonics-based computing or quantum computing. But we don't know if it's 2 or 15 years out. And Jonathan Carter is here to share an exciting way to leverage quantum computing in the short term with quantum simulators. And quantum simulators could totally change our understanding of chemistry and revolutionize material sciences in ways that could affect climate change and resource shortages. So Jonathan Carter, I'm glad to have you here with us. He's the Computing Science Deputy Director at Lawrence Berkeley National Laboratory and is charged with looking at post-von Neumann computing architectures. That's a pretty tough job. Now, Jonathan, before we get to quantum simulators, for the technologists, investors, and policymakers in the room, give us a way to think about the practical applications view and the use cases with quantum information science broadly.
Sure. Before I do that, so I'd really urge you to check out that Justin Trudeau video, because it's a really great explanation of quantum computing from a politician. So
it was probably rehearsed.
I'm sure it was.
Yeah.
So let me kind of back up and look at quantum information science, which has been developing now for 20 or 30 years, I guess, from a very high level. And I want to divide it up into kind of 4 pieces. And the first piece is quantum computing, which people have been talking about for a long time. I guess it got a lot of traction in the media when the MIT mathematician Peter Shor came up with an algorithm that would execute on a quantum computer that would factor large numbers into their prime factors in a polynomial amount of time, as opposed to current algorithms would take an exponential amount of time. So people started to talk about it at that point. It's probably a good many years away. There are a lot of technologies that one can use as qubits, but they have various drawbacks, and things like Shor's algorithm rely on a large number of perfectly functioning qubits, qubits that are error correcting. And we're not anywhere near that yet. So computation is one facet. So just let me take a quick diversion here. So many of you will know that there is a quantum computer manufacturer which is currently selling devices. The name is D-Wave. They're selling a certain kind of quantum computer. I would kind of classify it in this computer space. It will solve pretty specialized problems, not general quantum computational algorithms, but I mention it and put it in that category. Another category, quantum information science, is communication. So recently, I guess 2 or 3 weeks ago, maybe a little longer, some of the tech journals reported that China had launched a quantum communication satellite that would have explicitly encrypted via quantum mechanics communication channels between the satellite and the ground station. So quantum mechanics offers these possibilities of encrypting information much more strictly than current encryption technologies like RSA, and then you can also tell if the stream of data has been intercepted. So communication is the second piece. Third piece is metrology, so measuring things. We had a talk earlier today about sensors. It turns out that these little qubit devices can really make excellent sensors in some cases. And one case I'll just mention is if you take diamond and you knock out 2 nitrogens, knock out 2 carbons and you put in a nitrogen, this little nitrogen and vacancy in diamond is a really exquisite sensor of magnetic field. It's an incredibly delicate magnetometer. And some people have even suggested that this is a way birds can direct themselves, that they have this inbuilt compass. But in any event, nanodiamonds with these features are becoming really ubiquitous as a kind of a sensor. They're non-toxic, and you can infer the local magnetic field by the color of the photons that the diamonds emit. So they're really, really cool sensors. And the final piece is going to be the main topic of today, which is quantum simulators. And I kind of want to define quantum simulators as we're going to take the qubit technologies that we have now and some of the applications that we want to solve, and we're going to co-design an algorithm and a computational device that takes the best advantage of current algorithms and current qubits. So we're not going to hang around for 1,000 qubits that are error-corrected, that can withstand 1 million gate operations on them. We want to be able to do something now. If it's more approximate, that's okay. We think there are some great use cases for even these approximate methods.
Yeah, it's really exciting. And right now in quantum simulation, it seems like it's all about chemistry, how we understand chemistry, and changing what we can do with chemistry through material sciences and applications. Why do you think chemistry is the key?
So there are a number of really compelling examples, I think, where if we had better ways to simulate chemical problems, we could have a really a big impact on society, on energy consumption. And I'll just kind of sketch one of them. So many of you, I think, will be familiar with an industrial process called the Haber process. It's a process where you take nitrogen from the atmosphere, you cook it up with a catalyst, high temperature and high pressure, with hydrogen, and you make ammonia. So it was invented at the turn of the 1900s, and the inventor, Fritz Haber, won the Nobel Prize for it, actually. It's kind of an incredible story. Lots of things have been written about this process. Some people have even said that it has been the major factor in producing the population explosion that we've seen over these past 100 years. The amount of fertilizer that you can make from ammonia as a precursor has enabled us to grow, vastly more crops and then raise animals and all these kinds of things. It's said that, I read this factoid that maybe 80% of the nitrogen in our bodies is made up of nitrogen that was made by the Haber process. So it's a great process in that sense, but it also uses between 1% and 2% of the world's energy supply. And that's not a good thing. We would like to improve on the energy efficiency of fixing nitrogen and making fertilizer. Now, it turns out we have a great biological example of a different way to do this. So some kinds of plants in symbiosis with various kinds of bacteria can fix nitrogen at room temperature and pressure using specialist catalysts, nitrogenases. Nitrogenases have really resisted current ways we have to simulate how they work. We have some crystal structures, we have some models of them, but no one's really quite sure what the mechanism is. And there's quite a lot of complexity in the active site. There are several iron-sulfur clusters, there's some iron-molybdenum clusters, and people don't really know how all the electronic states that are available here, how they factor into that. And this is a problem that current simulation techniques doesn't do very well on at all. It really fails to understand, to give us insight into how this catalyst actually works.
Yeah, and it's fascinating. For all that we know about chemistry, so much science is done based on intuition, just kind of a shotgun approach.
Right.
We know things about chemistry, but not why and how it works, because we're not effectively simulating it yet and predicting.
Right. I mean, it was kind of prescient. So Dirac, when he gave his Nobel acceptance speech, he said, basically, after my work and Schrodinger's work, all the laws of physics are now explained for us to understand the most of chemistry. The only problem, and he really, I guess, knew it was going to be a problem, is that the equations are so complex that we won't be able to solve them. And that's still true today. So chemists have been very very clever, and they've used their intuition, and they produce lots of different approximations to the fundamental theory over the past 50 years, and those have worked really well, in many cases. So if you're talking about thermochemistry of first-row hydrocarbons, that's a done deal. We know how to do this. But if you take these really exotic problems with lots of metals and lots of electronic states, we're still not very far along.
So you see all of these use cases with agriculture and energy and material sciences that we're only going so far because the chemistry experimental method is largely based on these old simulation or just intuition. So let's dive deeper into how quantum simulators work and what your team is trying to do to change the way we understand chemistry and how we do experimentation with it.
Right. So the idea is that we endeavor to use what we're provided for in the qubit arena. So for the chemistry simulations, we mainly use what are called superconducting qubits. And again, as an aside, those are the same kind of qubits that are used in the D-Wave machine. What you basically do is you take a little electronic circuit, maybe 100 nanometers, so actually pretty big compared with the circuits in all your laptops, cool it down to 20 millikelvin or so, and you put in a little, what's called a Josephson junction. It's basically a non-dissipative asymmetry in the circuit. And at these temperatures, the circuit behaves as a quantum device. So quantities that we normally think of as continuous, like voltage and current, they become quantized in this little device, and it shows energy level quantization. You can use it as a qubit. These things have not very long lifetimes, although the lifetimes have been improving a lot, maybe between 20 and 100 milliseconds, and you can perform operations on them, though in the nanosecond kind of regime. So you can do a couple of hundred, maybe 1,000 gates if you're lucky, and you can get a result. So what we've done is develop some algorithms for solving basically the master equation in electronic structure theory and chemistry, the Schrödinger equation, using qubits with this kind of fidelity. And so the algorithms that have been talked about in the literature really a lot up until now, the accuracy of those algorithms scales as one over the number of iterations required, number of quantum gates. So if you want an answer accurate to 10 to the minus 6, which is really what you need a million gate iterations, and we just can't do that. So we've come up with a couple of new algorithms where we're basically able to, by coupling this quantum simulator closely with a classical digital computer, we can do the things that are very easy for a digital computer to do on it. We can do the things that are very hard, like generating the wave function on the quantum device, and we flip between the two in a tight loop. So we generate some initial quantities, we get an initial wave function, we get initial energy out of the quantum device, we refine the classical coefficients a little bit, and we execute this tight loop. And there are some fundamental theories that say that the lowest energy that we get is the best wave function, and that we can go on and calculate all kinds of different properties with that.
So instead of waiting for the most powerful quantum computer you would need to do this, you build a quantum coprocessor with this quantum simulator and a more classic computational architecture. And as Larry Smarr said, this is a terrible, scientifically inaccurate metaphor, but it's a metaphor. It's like the quantum simulator is the right brain doing more of this ambiguous calculation, and the classic computing architecture is like the left brain. Yeah. You can start to do more advanced computational use cases right away.
Right. That's a good metaphor. We're really, quantum computers are really hopeless at doing things like addition and subtraction. You just, why would you wait for a device, to be stable 10, 20 years hence, when you can actually put the devices we have in the lab now to good use? Maybe at this point I could talk about another use case in a slightly different version of a simulator. So another problem that we're interested in is the problem of making really good magnets. So a lot of the great magnetic materials we have today use rare earth materials. And while they're not really rare, they're actually very difficult to extract. And they're also actually rare in the sense that I believe there's no working mines extracting rare earths in the US, for instance, at the moment. So they're kind of geographically concentrated, and they're expensive to produce. And they're kind of a limiting factor on producing these magnetic materials. So there's some interesting minerals that don't contain rare earths. And there's one that has a great name, Herbert Smithite. And Herbert Smith was a mineralogist who worked in the early 1900s. He actually predated the discovery of this mineral. But this mineral has a very unusual magnetic structure. And it's kind of defied explanation. People have called it a spin liquid. So what happens is that there's a lot of spin states in this crystal that have almost the same energy. The electron spins that give rise to the bulk magnetism have lots of different degrees of freedom and different ways they can point. No one really understands how this mineral has its magnetic properties very well. And we would like to, in case it leads us to some directions that we can produce our own versions of this in a synthetic form as really good magnets. So we don't have any good tools to simulate it at the moment, but we have this idea, which is a little bit more far-fetched than the quantum simulator I just talked about. But here's the idea. So as well as superconducting qubits, we have other kinds of qubits we can generate at the lab. And a great kind of qubit is an ultra-cold atom. So you laser cool, say, an alkali atom like rubidium or cesium or something like that. And then you trap it in a set of potential wells which are formed by intersecting laser beams. So the potential well you can think of maybe is a little bit like an egg box shape, and the atoms sit in the dimples in the egg box. And we can control what this lattice looks like, and we can give it the same geometry as Herbert Smithite, for instance. Now the atoms act as natural qubits. They are quantum, in and of themselves, and their spin interactions may offer insight into way the spins are interacting in the magnetic mineral. So this is called, in some cases, analog quantum computing, because we're building a system in the lab which evolves in an analogous way to the system that we want to simulate out there in nature. So we have these two different kinds of ways we can co-design quantum simulators depending on the problem we face and the technologies we have in the lab.
So you build this laser lattice quantum simulator or computing device to basically find out how that atom will respond and predict, and then compare that spin and its interaction to the prediction and get a more and more refined model of how that atom should or could behave. Is that correct?
Right. So the bulk properties of the atoms trapped in the laser lattice will resemble the bulk properties of the spins trapped in the crystal lattice. That's our hope.
So there's all these big companies like Microsoft and Google that are chasing through funding and putting talent behind a general or universal quantum computer. And what you've identified and what your team has worked on is this possibility of more near-term or mid-term quantum simulators. Why do you think these companies are focused on the general purpose quantum computing and not realizing these near-term possibilities?
Well, I think part of it is, so many of these companies are also getting federal sponsorship. And at the moment, most of the federal sponsorship is in the realm of both communication and universal quantum computation. Because, well, Shor, getting a device that will be able to use Shor's algorithm to crack RSA, in a sub-second is a very compelling use case for the intelligence agencies. And so they're spending money on that. I think that some of the companies, in fact, Google particularly, they're coming around to thinking that it would be quite nice to have a midterm win, as it were, with a quantum simulator, as well as pursuing the the long-term ranges. So I don't see our work as completely independent from it. And in fact, we know the Google group pretty well, and we frequently exchange results and insights with them. I mean, I'm not convinced, although maybe this is not correct, that a quantum coprocessor may be commercializable in the very near future. The idea we have actually is something a little bit different, which maybe I can talk about a bit later or even now.
Yeah, well, I just think it's fascinating to see all of these. We're all kind of caught up in the Time magazine cover stories about these new types of computing paradigms and architectures, but it's hard to drill in on what's the roadmap that gets us there and what are the near-term possibilities that don't fully realize necessarily like universal quantum computer, but could be really useful for things like battery manufacturing or material sciences.
Right. I mean, one thing to point out is that the innovations in the basic qubit technology that we'll be investing in will help the ultimate goal. So they're not dissimilar. It's just that we want to get to some usable simulation results in the near term rather than designing algorithms that will require many millions of gates and logical qubits.
Yeah. So you formed a really fantastic interdisciplinary team at Lawrence Berkeley National Laboratory. Tell us where you're at and where you think this is going from a development and a funding and a sector collaboration standpoint.
Sure. So I should really give a shout out to the team. So there's a group of people, one of which is I'm one of them, who's basically trained in classical digital computer simulations in the chemistry materials field. And facing what's happening with Moore's law and the power consumption of large computing devices, we were kind of charged with finding something new. So we looked to our colleagues in the material sciences division and the chemical sciences division, and they were using devices that turned out to be great qubits for their own really interesting fundamental chemistry and physics experiments to do with the nature of quantum measurement and various things like that. And we got together and we thought, well, how can we kind of change direction with a limited amount of money and look at some of these possibilities? So, to name a few people, we have Irfan Siddiqui from the Quantum Nanoelectronics Lab, Dan Stamper-Kern, ultra cold atoms, aficionado, Hartmut Hefner, cold trapped ions. I mean, we really have, in terms of where I'm sitting, we have a really dream team of great scientists who can manipulate these devices at the quantum level, and also a crew of theorists and computer scientists who can kind of bring it all together. One thing that's inspired us is a DOE program that started about 10 years ago, which was nanofabrication facilities, and the one at LBL is called a molecular foundry. And the model is that they put up nanofabrication instruments and technology to use to measure and quantify nano devices, and it can be really cutting edge. And people can come to the foundry, commercial companies, other researchers, and the people who work at the foundry will work with them with the equipment. And we think that quantum simulators are at a very similar place. They're not really, you can't really build your own, for instance. I think, or very, very few people can build their own SE qubit device. But we think an umbrella organization that will have various kinds of qubit technologies in a lab, and these qubit technologies can be covered with layers of abstraction which are easier for other domain scientists to understand and will form a kind of a uniform interface to these quantum simulators. And then we can just really see what works best for each interesting simulation challenge.
If anyone has any questions, come on up. But I think that's such a fascinating possibility to create a quantum foundry and a collaboration to basically give scientists an API into this kind of research.
Yeah.
Now, to me, what is really exciting about this, Mark, do you have a?
I got a question.
All right, Mark's got a question.
Hi, Jonathan.
Hey, Mark.
Grégoire Rabordi, who did the first commercial entanglement communications device in Switzerland, was with us at FiRe a long time ago. And we had a beach party. And he had said on stage that it's impossible to hack into that communications channel, like as you just said, because you could detect that hacking. And I said to him on the beach after a couple of beers that I thought I knew how to do it. And I told him my idea, and he said, yeah, that would work. So I'm curious what your opinion is of the actual integrity of that system, or whether we just think it has integrity and actually there's a way to break it.
Right. So I somewhat glibly towed the party line when I was describing those four quadrants. There've been a number of reports of people who have put forward algorithms that will defeat many of the commonly articulated ways you can use entanglement to secure your data. So, but I think it's a kind of a catch-up game that people are also improving the protocols for the quantum entanglement. So I think you may be in the you may get into an arena where it's only secure for so long, and then you need to think of another way to encrypt.
So yeah, we've got time for maybe one or two more questions, but I just want to call it how important I think this sector is, and we've heard a lot about the challenges with big flows of data and how we can solve big problems with them. But I think as a technology community and as a public at large, we're at this moment where there's so many fluff pieces in the media about new computing architecture and making a lot of promises. And I think that it's really important to find these nuanced and subtle and substantive examples of what are the near-term instances, research, and possibilities, whether it's neuromorphic computing or quantum computing or photonics-based computing, because that's going to be key to finding the investment and the research and the tangible opportunities, instead of just throwing MIT Tech Review articles back and forth for another 5 or 10 years and not really knowing where the space is. So there's some really interesting, very real technology and possibility happening right now. And Jonathan, what in this space are you most excited?
We
We got one more question.
So just a quick, so Jonathan, I was really excited to hear about the nitrogenase example. Did that work to your satisfaction in such a way that you're interested in going after additional biomolecules? I mean, 40% of genes, we have no idea what they do. And even for just the ones we think are enzymes, that kind of insight would be amazing.
So I guess I didn't. That's a goal.
Okay. I was
right.
wondering how much.
So I was about to kind of circle back. So I should give you kind of the state of where we're at now. So for superconducting qubits, we can have between 5 and 10 working. We have a new chip design that we've actually used the Molecular Foundry as a partner in. We think we can get to 100. If we can get the engineering right for that, then I think we can really scale, and nitrogenase will be right front and center on the radar. But it's now almost an engineering problem. It's very difficult to get all the control lines in without perturbing the qubits too much.
Great. Thank you so much, Jonathan.
Thanks.